Okay, so we have been describing the behavior of gas molecules in terms of kinetic molecular theory. And we've been using this theory to help us understand help us explain the various gas laws, whether it be the ideal gas law or any of the individual gas law like Boyle's law or Charles's law, etc. And this again, is a theory that explains gas behavior in terms of the behavior of the molecules at the molecular level. And we've made some assumptions here, namely that gases consist of a large number of molecules that are in constant random motion. And the volume that each individual molecule occupies relative to the volume of the container is insignificant. So we basically ignore the volume that each molecule occupies, and that we also ignore the intermolecular attractive forces between molecules. And these assumptions, while they may seem a little bit strange, really are true of real gases under ambient conditions, that is, relatively low pressures and relatively high temperatures. And importantly, making these assumptions makes our mathematical treatment of the behavior of gases quite simple. Okay, now we've seen some animations that sort of show us this behavior during class at various times during the week. And really what we've seen is that as the temperature increases, we see an increase in kinetic energy. Remember that temperature is a measure of the average kinetic energy of molecules within a sample. And one manifestation of this is as kinetic energy increases, we see that the velocity increases. That is, kinetic energy is 1/2 mv squared, where v is the velocity. Okay, we often, when we describe gases, we'll describe what is called a root mean square velocity or a root mean square speed, and this is the speed of a gas molecule with an average kinetic energy. Okay, and again we describe it in much the same way that we do kinetic energy, where kinetic energy here is this epsilon. This is 1/2 mu squared, where u is this root mean square velocity. Now in a sample of gases, as we have seen, at a given temperature, the gas molecules are in, again, constant random motion. So they're moving around. Some of them are moving quite slowly, like this guy, and others are moving very rapidly. But if we look at the distribution of molecules, that is the distribution of speeds, on average, most of the molecules have some average speed. I don't know why my animation is not working. If we increase the temperature, we will see an increase in the overall speed of our samples. This animation is not working. Let's see if we can reload this. Try this again. Okay, so here, say we're at 300 kelvins, and again, all of the molecules are not moving at the same speed. Some of them are moving quite slowly, some of them are moving very rapidly, and I can't even point to any that are moving so rapidly. And if we look at the distribution of speeds, some of them are, again, moving very slowly, a very small number are moving very rapidly. Most of them are moving with some speed that is close to what we call the average speed. And we often will calculate this average speed in terms of this root mean square velocity. Now, if we increase the temperature of our sample, what we see in general is that our molecules will start moving around faster in general. Again, increasing the temperature is increasing the average kinetic energy. Yes, there are still some that are moving very slowly, and again, this is borne out by our histogram over here, which as time goes on, we'll see that some of them still have very slow speeds, which is low kinetic energies. Some of them are moving very rapidly, but again, we have a distribution, and this histogram is not refreshing quite right here. But we get the idea. And again, if we would slow down, we would of course expect that on average our molecules would slow down. And that's exactly what we see. However, even at this low temperature, some of these molecules are still moving quite rapidly. It's just that most of them, on average, have slowed down. That is, they have an average kinetic energy that is lower. Okay, and again, the kinetic energy is directly proportional to the square of the speed. So at a given temperature, we can describe a distribution of speeds shown by these curves. So at a low temperature, most of the molecules will have some average kinetic energy corresponding to the peak of this distribution, but none of the molecules at any given time are traveling at the same speed per se. As we increase the temperature, we see a shift in the peak of this distribution curve, telling us that on average the molecules are increasing in speed, and we expect to see an increase in this root mean square velocity, or root mean square speed. And so this root mean square velocity is a property that again takes the average of the speeds of the molecules. Okay, and so one way to describe the kinetic energy is in terms of the temperature. So the kinetic energy of a given molecule is 3/2 RT over Avogadro's number, where this is the ideal gas constant, and this is the absolute temperature. So for a mole of gases, the kinetic energy would be 3/2 RT. Okay. So when we describe the kinetic energy, what we're taking is a number of molecules, K molecules, and we're taking the sum of the square of their speeds, and we are then taking the square root of the average of those speeds, shown by this equation here. Kinetic energy of each particle then would have this kinetic energy 1/2 mu squared. So if we combine these two equations, okay, we can get a relationship between the velocity, the temperature, and the molar mass. So coming back to our animations here, I want to pause this. If we look what happens if we compare a mixture of gases, as shown here, at some temperature. Okay, so here's a constant temperature. We have a mixture of two different gases, the little red ones and the larger blue ones. By larger here, we're indicating that the blue gases have a greater atomic mass or molecular weight here. And what we notice is that, again, we have molecules in constant random motion, but what is very clear from this animation, which is an attempt to represent reality, is that most of the red molecules are moving significantly faster than the larger blue molecules. So the blue ones in general are moving more slowly, and the red ones are moving more quickly, even though they all have the same average kinetic energy. And so if we were to sort of look at a plot of the speed of our samples, right, we see a variety of speeds. If we follow one of our blue ones, as it moves around, it shows a variation in its speed. Every time it collides with something, it changes its speed, and the same thing is true of our red. But basically, on average, the red ones are moving faster than the blue ones. That is to say, the speed is inversely proportional to the mass. So the heavier molecules at the same kinetic energy will have a slower velocity or a slower speed. Now this is borne out in our equation for the root mean square velocity. And in our next short video here, I'm going to show how we use this relationship to calculate the root mean square velocity for any sample of gas.